the universe is under no obligation to make sense to any of us. So I'll be saying things and you'll say, that doesn't make sense. Just remember what I just said, okay? Okay. What we've learned is that the universe is what we measure it to be, not what we want it to be, not what feels good, not what only has to make sense to our five senses. Here's what goes on. If matter and energy can go back and forth, this is how that works. I have a blob of energy and it decides that it wants to become matter, and it does. So all this energy becomes matter. If the temperature drops too low, then it's not going to happen. The energy will stay energy, and whatever matter was around at that time will stay matter. So watch what happens. We now have high enough energy that if you converted this pocket of energy into mass, E equals mc squared, you get enough mass to create particles out of it. Okay? So get a very low, take an electron, for example. That's very low mass among subatomic particles. So you can ask, how much energy does it take to make an electron? Write that number down. If you don't have that much energy around you, your energy will never become a particle. Ever. Okay? So, in the early universe, there was so much energy, every particle could be made. So watch what happens. You have a pocket of energy, it becomes mass. And the only way we know that can happen is if it becomes a particle and an antiparticle pair. Matter and antimatter.
Antimatter is the opposite of the first thing?
Yes.
Oh.
In every measurable way.
Huh.
Okay, so the opposite of an electron is a positron. It looks just like an electron, but among other things, it has the opposite charge of an electron, positron. Okay? Every particle has an antiparticle.
Does a neutron have an anti-neutron?
Yes.
Does a proton have an anti-proton?
Yes. And so you might say, well, what's the opposite charge of a neutron? Because a neutron has no charge.
Yeah, I know.
But you look at what the neutron is made of. It's made of quarks that have fractional charges that cancel each other to get zero net charge on the neutron. So an anti-neutron has all those same quarks, but the antimatter version of those quarks on the inside. If you take matter and antimatter and put them together, they annihilate and become pure energy, and the matter disappears entirely. That happens all the time in the center of the sun. It happened everywhere in the early universe. Now here's the rub. You have all these photons of light. Oh, by the way, I have a photon joke. Photon checks into a hotel. The bellhop comes up and says, do you have any luggage? And the photon says, no, I'm traveling light. All right, so a photon turns into matter. It's a matter-antimatter pair. Matter and antimatter come together, they make a photon. It's symmetric, okay? So you have all this energy in the form of photons becoming matter and back and forth, and there it goes. As the temperature of the universe dropped, you reach a point where you can no longer make particles with the energy you have. But you have all these matter and antimatter particle pairs that eventually find one another and annihilate and make a photon. But we're still cooling the universe. So, according to our known laws of physics, in the cooling universe, every matter and antimatter particle pair would have annihilated, made a photon. The photon would have cooled, and no more matter would have been made, and we would have had an entire universe of just light. But that is not the universe we occupy. Mysteriously, we call it symmetry breaking, just because that's what happened. We're just describing what happened, not that we fully understand why it happened. One out of basically 1 million of these reactions, 1 out of 1 million, the photon did not make a matter-antimatter pair. It just made a matter particle.
What, it was very...
You're trying to find out why.
Yeah.
And I'm just saying, it is that. okay? So, 1 out of about a million makes a matter particle without the antimatter counterpart. So now the dance card, the dance hall, has 999,000 partners, and there's 1 left over. So everybody else becomes light, and that one has no antimatter particle to mate with. And it is frozen out of the universe and has become all the matter that we know and see today. In the concept of multiverse, we would have many, many universes. All the laws of physics don't have to be the same in each universe. So there could be plenty of universes where the dance card was full and they just have light in them, and you are not in that universe saying that it was just a chance occurrence.
Oh, well.
You are in the universe where it happened.
I don't care about the other ones. I'm just interested that our universe, the one that we know and live in, is such a fragile arrangement originally.
No, it's not. Well, it doesn't have to be. It may be, but it doesn't have to be,
Yeah.
and it is unlikely to be. And can I give an obscure example that will settle this?
Yeah.
Okay. Line up 1,000 people and give them a coin, and everybody flip the coin. And about half will get tails, half will get heads. If you got tails, sit down. That's 500 left, approximately. Mm-hmm. Have them flip. Half get heads, 250 of you sit down. Now we're left with 250. Do it again. Go from 250 to 125 to 60 to 30 to 15 to 8 to 4 to 2 to 1. Okay? In this experiment. It's not an unthinkable experiment. Mm-hmm. This person who survived this exercise flipped heads 10 consecutive times. Now here's what journalists do. They go up to that person and they say, how do you feel? Well, I knew I had felt that head's energy halfway through, and I was feeling it, and did they ask anyone else if they felt that head's energy? No, they only interviewed that guy. Okay?
You come
Wait,
on to...
I'm not done.
All right.
Wait, so that person says, boy, I was lucky to flip heads 10 consecutive times. Well, essentially every time you do this experiment, somebody's going to flip heads 10 consecutive times. So you want to say, oh, this is a special universe in which that happened? No, because of the nature of the fact that you have 1,000 experiments happening all the time, there's going to be one where somebody flips heads 10 consecutive times. Every time you do this experiment. That does not make it special. Just because somebody flips heads 10 consecutive times every time you do the experiment. So you're in a universe where this weird thing happens at the beginning, and you want to feel all heads energy about it. And I'm saying, in a multiverse, there could be 999 universes where that did not happen. And you're in the one that did, and you want special credit for it. I'm not giving it to you. So you look up, and the planets are going forward against the background stars, and then backwards, and we call that, there's a word for that, retrograde, and they do the loop-de-loop, and nobody understands it. Newton comes along, writes down equations of motion, equations of gravity, and kind of on a dare, he invents integral and differential calculus. Then he turned 26. This is why Isaac Newton is my man, okay? Just to make that clear.
Okay.
Among many reasons. But so he writes down these equations, and he can now demonstrate full knowledge of how, why, and where, and what the planets are doing. And so potent was his new theory of gravity that it worked for moons of Jupiter orbiting Jupiter, not just planets orbiting the sun. And this was the first indication, maybe this is not just a local truth, that maybe it applies across the universe. When we have storms, it's in our atmosphere, so that's gas.
Yeah.
We rotate once a day, and so that rotation creates what we call a Coriolis force, which moving air that moves from one latitude to another, actually has its direction deflected because of this Coriolis force, and this is why storms rotate in one direction counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. Just a quick aside, I was channel surfing one day, waiting for a movie to come on at the top of the hour, had 15 minutes. I hit a football game, and they just ended the game at a tie, and they just started overtime. I said, that's about right. Let me just watch this. How bad could it be? After the necessary exchange of possession, it became sudden death overtime. And then one of the teams, Cincinnati Bengals, got within 50 yards, and they kicked a field goal. And the ball rotated up. It hit the left upright of the goalpost and went in. And I said, ooh, wait a minute. And I said, which stadium is this? What's the latitude? And I looked at the orientation of the stadium, I did a calculation, and then I tweeted. And I said, the overtime winning field goal by the Cincinnati Bengals was likely aided by a 1/3 of an inch deflection to the right imparted by Earth's rotation.
Which
People lost their minds. People, the local sports channels, and so the point is, if you were going north-south at all in the northern hemisphere, you will deflect to the right, no matter what you're doing. Okay? That's why you have a low pressure system, and I'm a ball of gas below it. If it's low pressure there, and I'm air, I'm going to head for the low pressure. That's how this works. It's low pressure. That means there's higher pressure out here. So all the pressure is going to send me in that direction. But I'm crossing lines of latitude. And so Earth's rotation will deflect me to the right. How about air that's above it? It says, I see a low pressure system. Let me go to it. So it goes to it, and it deflects to the right. So all this air deflects to the right, but it's still trying to get to the center of the low pressure system, but it can't because it keeps getting deflected. And all this deflection becomes this cyclonic energy that turns into a storm. And that is how you get hurricanes, tornadoes, what do you call it? Cyclones.
Cyclone.
Okay.
So we're back at Jupiter finally.
Yes, we are.
Yes.
So now watch.
Oh, good.
So this happens in the gas.
Yeah.
All right. The Coriolis force is heightened if you spin faster. Okay? And so what is Jupiter? It's 100 times bigger than Earth. More than that, 1,000 times bigger than Earth. It's like, it's 10 times across, cubed. So it's 1,000 times bigger than Earth. It's mostly gas. And it rotates once in about 10 hours. You want to talk about ferocious Coriolis forces? We have storms that last weeks here. Hurricanes that pick up and they go weeks on this little speck we call Earth that has this much atmosphere on it. Go to a planet that rotates twice as fast, is 10 times as wide, 1,000 times the volume, and is mostly gas, and you're complaining that it lasted 300 years?
You are really good. All right,
No.
What is a dwarf galaxy?
It's a little galaxy.
Well, that I figured.
Didn't we go through this already? Our words mean what they say?
But
we're past that already.
There are galaxies that you see, the ones the Magellan saw, smudges in the sky. Those are huge things.
No, well, they're dwarf galaxies.
Those are dwarf galaxies?
Oh, yeah.
Oh.
Oh, yeah, they're like 100th the size of our galaxy.
So how many dwarf...
They far outnumber big galaxies.
They do.
Yeah, so maybe we shouldn't be calling them dwarfs, because they're the common size galaxy. We should just be called giants, perhaps.
Giants galaxy.
And they call them regular.
Right?
That's how that works, right?
What is the difference?
Right?
How
Like
many
that?
stars are in a galaxy?
Our galaxy has several 100 billion stars.
And in a dwarf galaxy?
At most, a billion, but more typically hundreds of millions. These are small numbers compared to full-up red-blooded galaxies. So tiny are dwarf galaxies, and we tend to find them in the vicinity of big galaxies, but you know what happens? You know, they orbit the big galaxy, but their orbits are not stable, and they do a death spiral in, and they get eaten by the larger galaxy. And we have a term for that. It's called galactic cannibalism. In fact, there are streams of stars that we see in our own galaxy that have the same trajectory as one another through the stellar system that is the Milky Way. So and you follow it, and it comes back out and back in again. And so this is evidence that this was once a fleshy but dwarfy galaxy that we ate, ripped apart. And now the stars are just trying to have the last bastions of a memory of what they once were, because they're getting stretched apart by what we call the tidal forces of our galaxy.
Does the Milky Way have dwarfs?
Yeah, it has the first science essay I ever wrote was called "The Galaxy and the Seven Dwarfs," because at the time the Milky Way had 7 dwarf galaxies in orbit around it, and then but dwarf galaxies are very small; they're hard to detect. And since then, we've discovered, a couple dozen more. So we might be up above 2 dozen dwarf galaxies in our vicinity, basically nearby. So the point, getting back to the void, is you look out in the void and say there's nothing there. Well, what are you invoking to declare that it's a void? Is it your eyes? Well, let's bring in a telescope. Are you using visible light? Is that a visible light telescope? Bring in an X-ray telescope, an infrared telescope. Bring in the spate of senses that science has developed that transcend the 5 native senses we have through our human physiology. And that power enables us to decode the universe.
There's this moment where somebody has to figure out that there might be something redder than red or somehow more than violet. Now, we only have eyes, but this particular person used a thermometer.
It was brilliant.
It was brilliant.
Brilliant.
Yeah.
Okay, so Isaac Newton is the first to understand that white light is composed of colors. So he takes white light, puts it through a prism, and he gets Roy G. Biv. Actually, the indigo, he had a mystical fascination with the number 7, so he wanted to lay down 7 colors. But indigo is just really blue-violet, all right? Okay. But anyhow, we'll give him his indigo because he did all that stuff before he turned 26. So if you invent calculus just on a dare, we give it to you, all right? We'll give you indigo if you need to have indigo. So he's got the colors, and then he took those colors, merged them back together, and he got white light out the other side. That's some freaky stuff. That's just freaky.
Yeah.
That red, orange, yellow, green, blue, violet equals white. Okay. So we're good there. William Herschel comes around later and says, I wonder, just to even ask this question, I wonder if the different colors of light have different temperatures. So he laid down the spectrum with sunlight prism, and he put a thermometer in each color. And then he had an 8th thermometer. I don't know if he used one and did the experiment 7 times, but he had another thermometer that he used as the control thermometer. You put that over to the side where there are no colors. And that would presumably just measure the room temperature. So he knows enough to even think that this is an interesting exercise, and he's got a control thermometer. And he just puts it over to the side of the red, out of sight. And then he watches the thermometers. And the control thermometer goes through the roof.
Yes, it does.
And he's looking at it, and he says, something must be coming through the prism that I cannot see. And he describes this as light unfit for vision.
Yeah. Yes, he does.
He discovers infrared light with that experiment.
And then another guy
which the human eye cannot see.
It's
and if you go to the hardware store and get an infrared bulb, and you turn it on and it looks red, you're seeing the red light that is also emitted from this infrared bulb, and the heat that you feel, your eye cannot see, that's all the infrared that you're buying when you pay money for that bulb. Yeah.
And then some other guy put a piece of paper on the other side of violet, and it turned dark, and he pretty much
photographic paper.
Photographic paper.
And he found that it responded in the way you would normally respond by putting photographic paper in front of visible light. So he concludes, that was somebody else later.
Somebody else, yeah.
Right, and says, there's something beyond the light. There's something less than the red, infrared, something beyond the violet. And thus was discovered ultraviolet light. And so to pose the question in the first place was a stroke of brilliance. To then trust your measurements on a level where you then declare you have made that discovery is a whole other thing. Well, first of all, the universe is expanding, and there is more and more observable universe all the time. The universe at its edge is expanding at 1 light year per year. That's how that works. And so in 1 billion years, the edge is not going to be 14 billion light years away. It'll be 15 billion light years away. So we got that. Okay. So now, galaxies 13 billion light years away, we are seeing light emitted by that galaxy, and that light has been traveling for 13 billion years. Okay. Yes, that galaxy emitted its light when the universe was 10% its current age, and in fact was much smaller than it is today. The next telescope, the James Webb Space Telescope, is tuned to live in that regime, to find galaxies being born in the early universe. So there'll be a whole lot more data coming back from the early universe when that telescope gets launched, lands at its observing point, and gets turned on. So there's nothing you said that's odd or weird. That is the universe we live in.
Question is, can you help us understand a multi-dimensional universe? What would be the dimensions we are unaware of?
Any dimension higher than the 3 that we're familiar with, or the actual 4 that we're embedded in. We live in a 4-dimensional world. And that might sound a little flaky or freaky, but consider the following fact. You have never met someone at a place unless it was also at a time. And you have never met someone at a time unless it was also at a place. That requires 4 dimensions of coordinates.
Wait. What about in a dream?
Is the dream happening inside your head?
Yes. I don't know when.
So the only point is, we know intuitively that we need 4 dimensions to localize someone to meet up with them. Especially when, well, only 2 dimensions if you don't have tall buildings. You have tall buildings, you need the 3rd dimension. So you don't say, I'll meet you at the 20th floor of, on 721 Park Avenue. What time? Okay? There's a full 4 dimensions going on there. So I want to convince you we live in a 4-dimensional world for that reason. Okay. It may be that these 4 dimensions are manifest to us, but that in fact we are embedded in a higher dimensional space. And string theorists on the frontier of this exercise are hypothesizing at least 10 dimensions to account for everything we see in the universe, even if we do not directly measure those dimensions themselves. Now, with your permission, may I go on a dimensional journey with you? May I? Might take you on a journey?
A dimensional odyssey.
Odyssey. Are you ready?
Yes.
Okay. Are we ready? Just get ready for this. Okay. So, I'm at my desk, and the desk is a surface, okay? And I start putting pages down on the desk. I'm tiling them on the desk. And then I run out of room. I have exhausted the 2 dimensions of the surface of my desk. We have ways of accommodating this problem. And so we have page organizers that go upwards. So now when I don't have any more surface area of the desk, I can enter a 3rd dimension and put pages there. If you are an ant embedded in this 2-dimensional world of the surface of my desk, and you fill up the desk with these sheets of paper, the ant will say, "There is no more room." And I say, "Yes, there is. Watch me." And I take a piece of paper off the desk, put it in the page organizer, and according to the ant that's embedded in the 2 dimensions, that page disappeared. It disappeared into a dimension that ant does not have access to. What a brilliant invention this is. You can put practically an unlimited number of pages, far more pages above the desk than on the desk. So access to a 3rd dimension is an extraordinarily useful storage device for a 2-dimensional creature.
Does the ant trust you that what it cannot see is nevertheless there?
You have to then talk to it about this extra dimension. And then it will have to just trust you.
Yes.
Because watch what happens next. I now have my 3-dimensional room, and I'm filling it with boxes. Now I've run out of space to put the boxes. But now a 4-dimensional alien looks at us and says, "I got this. Just move it into the 4th dimension." What are you talking about? And the alien comes in, reaches in, takes one of the boxes, and then the box disappears. Disappears. It went into a 4th dimension. And this was captured in the film Monsters, Inc. Did you guys see this film? These are monsters that work in a door factory, and they make these doors, and they open the door, and it is the door of a kid's bedroom or their closet. And they step through, and they're in the kid's closet. And then they scare the kid, because that's their job. They're monsters. Okay? This doorway is a portal through the 4th dimension and then back to the 3rd. So imagine a new storage system where you just go to Home Depot and buy a door. And that door is your portal to a 4th dimension. You open the door, put your boxes, close the door, and you look on the other side of the door, there's nothing there. So this is what's going on when you have access to higher dimensions. There are things that happen in quantum physics that kind of defy our sensibilities. Like particles pop in and out of existence. They defy any rational attempt to understand it. Particles can be entangled with one another. A particle can be here, and there's a barrier, and it can spontaneously show up on the other side of the barrier at faster than the speed of light. All of this is just mysterious. Let me ask you. Suppose you have a sphere, and I live in a 2-dimensional world, and you take this hollow sphere, so it's a shell, and you pass that sphere through my 2-dimensional universe. How will I describe that? I will say, this point just appeared out of nowhere. Oops, now it's a circle, a small circle. And that circle's getting bigger by the moment. Oh my gosh, it reached a maximum size. Now that circle is just shrinking. It's shrinking. Now it's a point. Now the whole thing disappeared. This would be completely freaky to a 2-dimensional being. But it makes complete sense if you live in 3 dimensions and you pass a sphere through my universe. So, who is to say that some of the mysterious things we are describing accurately, but don't otherwise make sense in a higher dimension? And these are just the manifestations of higher dimensional phenomena in our world. And that's an aspect of what these higher dimensional physicists are trying to establish.
At this point...
Now I want to totally blow their minds, if I can.
Oh, sure.
If I may. But you got to stay with me on this, okay? A point has no dimensions. There's no height, width, depth, so it has 0 dimensions. A line has 1 dimension, length, okay? A square has 2 dimensions, sort of height and width. A cube has 3 dimensions, height, width, depth. We got this. Now follow me. a line is one-dimensional, but it's bounded by two zero-dimensional things. Those are the points. One dimension bounded by two zero-dimensional points. A square is two dimensions bounded by four one-dimensional sides. A cube is three dimensions bounded by six two-dimensional sides. So in other words, the dimensions of your sides are going up. Your line is bound by zero-dimensional points. Your square is bound by two-dimensional lines. By one-dimensional sides. The cube is bound by two-dimensional squares. Okay? So we're going up 2, 4, 6. 2 points, 4 sides of a square, 6 sides of a cube. And each side is one dimension less. They're squares on the sides of a cube. They're lines on the side of a square. They're dots on the sides of a line. Let's go up to a 4-dimensional cube. A 4-dimensional cube has 8 sides. A regular cube had 6 sides. We're going up by 2. A 4-dimensional cube has 8 sides. And each of those sides is a 3-dimensional cube. One dimension down from itself. In the same way, each side of a 3-dimensional cube is a 2-dimensional square. So when you get to 4 dimensions, the sides are 3-dimensional surfaces. And you can take this all the way up. And our brains can't picture what we call a hypercube, in some circles a tesseract. We can't picture a volume bounded by 3-dimensional cubes. What does it even mean? This is because we evolved in the plains of Africa, just not wanting to get eaten by a lion. Our neurosynapses are ill-equipped to do the distance on this. And this is why we invent mathematics that can take us there.
Well, the mathematics can help us imagine it, but if we want to credit it with reality, then you have to design an experiment that somehow touches your own world.
Yes, yes. So you can invent something that you can't see if it has testable consequences in ways that you can see. That's perfectly allowed. Not a problem. Mm-hmm. Oh, and by the way, there's some people that say you cannot prove a negative. Some people like coming after. Generally, you won't hear a scientist say that. Mm-hmm. It's others, like philosophers and people who like criticizing scientists, but who are not scientists. They'll say you can't prove a negative. We kind of do that all the time, okay? But we don't use the word proof. We demonstrate without any further discussion that the negative is true, okay? So here's an example. There's a cave there. Is there a bear in the cave? I don't know. I'm not going in to find out, okay? I'm going to set up cameras and see if a bear comes out, okay? So I set up the cameras all throughout summer. No bear goes in and out. But then I take down the camera. Maybe a bear went in there to hibernate. So here's what you do. You set up powder outside of the cave, something that will record a footprint. And you just monitor this month after month after month after month. Do it for 12 months. Look up in the charts how often a bear has to eat and how long it would take a bear to die for not eating. If the period of time you waited is long enough so that there are no footprints, you conclude that there is no bear in that cave. I just demonstrated a negative sufficient enough for me to no longer pose that question and go on to another problem. But if you are so distracted that it's not a formal proof of a negative, then you could just keep sitting there wondering while the rest of us decode the nature of the universe. I wonder if, in fact, the human intellect is sufficient to actually decode the full operations of this universe in which we live. And it's not specifically an astrophysical question, it's just more, we are an intelligent species because we defined ourselves that way. We don't have the benefit of another species to compare ourselves with, against whom we might fail miserably. And so when we compare ourselves to chimps, we sit up righteously and say, we have poetry and the Hubble telescope and philosophy, and the chimp just stacks boxes to reach a banana. Yet there's only 1% difference in our DNA. But then you'll say, what a difference that 1% makes. And I would say maybe that 1% DNA difference corresponds with an equally small difference in the intelligence between a chimp and humans. And you say, I can't believe that. No. Well, imagine some other species that visits us that's 1% along on that same scale, smarter than us. Consider, the smartest chimp does what our toddlers can do. And there's no way you will explain to a chimp, I'll have dinner ready at 6:30, can you pick up some juice on the way home? The simplest human thoughts are inconceivable to a chimp. And their talents are about what our toddlers can do. So let's get back to this 1% smarter alien that we've discovered. Corresponding this analogy, we now say, what would we look like to them? Well, they would roll Stephen Hawking forward after combing the human species, and they'd say, this one is slightly smarter than the rest because he can do astrophysics calculations in his head like little Timmy over here, who just came home from preschool. Oh, Timmy, you just composed 3 sonnets. Isn't that cute? Let's put it up on the refrigerator door. Oh, you just derived the fundamental law of calculus. Isn't that cute? Put it up on the refrigerator. Their simplest thoughts would transcend our deepest thoughts. And maybe to them, it is obvious what dark matter is and dark energy. Maybe to them, particles popping in and out of existence is a trivial exercise in their understanding of the multidimensional space-time continuum. And we are here groping at the sides of a wall, not knowing how tall, wide, or deep it is, because we have the limits of the human physiology evolved off the plains of Africa just to try to understand the entire universe. So I lose sleep on that question each night. I think often about the questions we do not yet know to ask because discoveries yet to come, but when they arrive, will put us in a new vista, a new place to stand, enabling us to see questions undreamt of and unimagined before we got there. So when I, again, lay awake at night, I ponder what kinds of questions lay beyond our reach. Because the questions that we even know how to pose, they're there. Those are not even interesting to me anymore because we knew how to ask the question. I want to know the question that is beyond everyone's reach. And by definition, I can't, because we haven't gotten there yet. But that doesn't mean I shouldn't dream of that frontier.